Good morning, good afternoon, good evening, everyone. Welcome to the third day of our technical symposium of the Management and Sustainability of the Outer Space Activities Conference, organized by the Portuguese Space Agency and UNOSA. This will be our third and last day of this technical symposium, and we'll be starting our first session dedicated to space debris and space traffic management and the interconnection of these two topics. My name is Inês Dávila. I am the Space Safety Officer at the Portuguese Space Agency. I will be the rapporteur for this session, and with me I have Isaac Always from the Ministry of Business, Innovation and Employment from New Zealand, which will be our moderator. Thank you. The floor is yours, Isaac.
I Sorry, I've just got another sound coming through. Hi. Okay, sorry, I had the other live stream playing on my on another browser. So good morning, everyone. Good to see you all. Good to see the technology is working, and thank you very much to the Portuguese Space Agency, Portugal Space, for hosting this event along with the United Nations Office of Outer Space Affairs. Thank you very much for the introduction. My name is Isaac Hollis. I am a principal policy advisor within the New Zealand Space Agency, and I'm the New Zealand lead delegate to the Committee for the Peaceful Uses of Outer Space and its subcommittees. So I don't have a technical background. I take a policy approach to these issues. So I am really excited to hear today from three experts. So we've got some excellent speakers for you today. We have Tanveer Ahmed, we have Mike Lindsay, and we have Song Jaedong. So I will introduce them in more detail before they speak. But I just want to say a big thank you to you as listeners, a big thank you to you as speakers. And the format of the morning session will be that the speakers will have about 7 to 10 minutes to speak. They are welcome to use slides if they want. After all the speakers are finished, I will ask some questions, but we of course have the ability to take questions from the audience. If you have a question, you can place it in the chat and I will direct those to the speakers. So our first speaker is Tanveer Ahmed. Tanveer is co-founder and chief technology officer at Digantara. Digantara is a space situational awareness company which aims to bring together different types of data from multiple sources, including the company's own satellites. In this role, Tanveer leads the design and development of core space situational awareness capabilities. Tanveer, over to you.
And thanks for the organizer for having me here. I have a small presentation. I think I'll try to present my screen first. Is my screen visible? Can someone confirm that you are able to see my screen?
Yes.
Okay. Hello, everyone. So Digantara essentially is having a focus to map the space traffic. Space traffic essentially includes satellites and debris orbiting the Earth. In today's presentation that I would kick off with, I essentially have divided it into two parts. The first set of slides would be talking about the problem statement that is existing in the space industry, pertaining which is arising because of the increasing space traffic. I'll try to sort of demystify the whole problem of space debris and space traffic. And the second set of slides would be focusing on how the Digantara is focusing on solving this problem. So the primary focus is to create both hardware and software. The hardware is to track space objects, and the software is to use the tracking data through and utilize that tracking data for actionable insights. I'll cover what we do in more detail in the subsequent slides, but first let's talk about the problem. I think right now, the space industry overall is at a phase where a good amount of entities, agencies, and companies have learned the art of building, launching, operating, and safely disposing of satellite. And even all the startups and private companies are have completed their first set of technology demonstration missions and are looking for the second set of missions, which is towards scaling their space operations and launching more satellites and generating more data and more services for our customers. So this is leading to launching of more satellites. And for every satellite we launch, we create 10x or 100x objects in space. These are usually debris or other secondary objects associated with the launch. When we started launching in 1950s, it was just only one object in the space. Right now, we have over a million objects that are above centimeter in size that are orbiting Earth. And until now, the entire space uh, orbits were utilized under a presumption that space and orbits are infinite, which is which was a valid assumption until now. But I think we have surpassed certain critical points in our journey towards utilization of space. The firstly being, as of today, I think this is a milestone that we have reached almost a decade back, wherein even if we stop all the launches and space activities in space, we just stop launching satellites, the amount of object, the amount of traffic in space has already built to a capacity where the traffic can sustain itself. And this sustainably, I use this the word here, sustainability in a very challenging point of view, because even if we stop launching all satellites, the number of objects in space will continue to increase. And the challenge essentially is amplified by the fact that once a satellite is in space, it doesn't necessarily come down. I would like to take a few steps back and draw analogies to the roadways and airways. When the first uh, car was put on road in 1880s, and the first flight was taken in 1900s. Imagine those vehicles, those cars, and those aircrafts in their regimes as of today. Essentially, the first car that came onto the road is still on the road, and the first flight that took flight that we launched is still in it. The amount of traffic both on roads and in air would be humongous. And essentially, although that fact doesn't is not true for roadways and airways, that is very much true for a satellite. Anything that is launched into space stays there. Perhaps even the first set of satellites that were launched almost 5 to 6 decades back are still orbiting and will continue to do so uh, over the next few decades or even centuries. And another challenging aspects in this part is, and if a car or a aircraft dies, so to say, then it becomes still, it becomes useless. It comes off the road, it comes off the skies. But satellites don't stay there in their orbits, and rather they continue to orbit in an uncertain, tumbling environment. And today, if all satellite operators that are operating satellites know that we have reached the next set of next critical point, wherein collisions or conjunction warnings or uh, a satellite operator getting alerts that multi-million dollar asset in space that is orbiting, which was built over multiple years of efforts with a lot of financial with a lot of financial assistance of any capital access to the have. They periodically, regularly gets alerts saying that their satellite or spacecraft would is likely to undergo 10 or hundreds of collision in the matter of next few days. So this is the situation we are in. And I think the next step where we are going towards is orbital maneuvers. For maneuvers essentially change that the satellites have the capability to fire engines and change their orbital movements. So this process is called the maneuvers, and the instances of doing such maneuvers to evade collisions is going to be normal. We are going to see we have satellite maneuvers that satellites that would maneuver on a weekly or a monthly basis, and this is the situation as of now. And we are just one collision away from the situation becoming much worse than what it is today. Uh, Coming to Digantara, we are solving this problem in three ways. The first step is to gather tracking data. Now, this can be done by two ways. One is having hardware in space on satellites, and another method is to have sensors or hardware on ground. At Digantara, we are doing both. We are building satellites that can track space objects, and also we are building ground-based sensors that can track space objects. The idea is to have a hardware infrastructure that can track these objects in multiple ways. Why this essentially is needed is if we take any sensor, be it a ground-based sensor or a space-based sensor, these are essentially four types. It's either a optical telescope or camera, or a LiDAR, a radar, or a passive RF sensor, or a RF telescope. Essentially, these are the four sensor technologies through which satellites and space debris can be tracked, be it space-based or ground-based deployment. Each of these sensors have their own strengths and weaknesses. And will the if we think of space traffic as a data problem, the only way to solve it is to have multiple sensors and have the capability to associate these tracking data from different platforms into a single operational picture. So that is where the second set of solution come in. The second step of our solution comes in, wherein the data from different sensors uh, are taken and transformed into one single operational picture. For example, if we take telescope sensors, any of you who is an enthusiast of astronomy must would have experienced satellites coming in your field of view, or many of us, many of us would have seen the difficulties astronomers are facing because of satellites passing through the field of view. These are essentially when you take even phone camera, go to a high altitude region such as the Himalayas or and point your camera towards the sky, you'll be able to see streaks or lines in your image. Those are satellites. The space situational awareness sensor are a sophisticated mechanism of gathering that kind of tracking data. These are in its raw format. Essentially, it tells that an object is above you or slightly at 20 degrees from you. In second set of steps, we are taking that kind of raw information from individual sensors and transforming it into a single operational picture. This is where generation of space catalog comes into picture. Essentially, the whole raw data is transformed into a catalog, and that catalog is used to generate an operational picture. And that operational picture forms as a basic layer on which it's a basic fusion point wherein all data sources coalesce into a single operational picture, and the single operational picture is used for the downstream analytics. And the last step in our solution is utilizing this operational picture to generate actionable insights and analytics and data products for our customers that are primarily in launch activities, satellite operators, insurance companies, and government. So imagine you have you're a satellite operator. you'd want to know all the possible collisions that your satellite is likely to undergo, and among them, know which are the serious collisions. And once a collision is identified to be of a significant threat, how can we evade that particular collision? What will be the avoidance strategy? So this is one of the examples, and similar examples would exist across all the actors that are interested in utilizing sustainability solutions for space to make sure that satellite operations are safe. And at the end of the day, this whole three-step ecosystem three technology drivers that we are building is coalesced into a single operational center that anyone could use and gain insights in what's happening in space. So overall, at the end of the day, at Digantara, we are mapping space traffic and utilizing that maps for sustainable or to figure out how we can sustainably use space. So that is what at Digantara we are trying to do.
Fantastic. Thank you very much, Tanvir. That was a really interesting presentation. I'm sure that we'll have some questions for you at the end. I'd like to introduce the next speaker now. Sung Jae-dong is a senior researcher in the Space Situational Awareness Research Office at KARI. KARI is the Korea Aerospace Research Institute and is the National Space Development Organization of South Korea. Sung, over to you. Thank you.
Hello, everyone. My name is Jae-dong Sung. First of all, thank you for inviting me this great opportunity. So I have a PDF presentation. Let me see. Okay. Will introduce about KARI's activities on SSA and STM. So my name is Jae-dong Sung, and I am the flight dynamics engineer and responsible for operation of conjunction analysis software. So this is the mission status of KARI's LEO satellite. So as you can see, the gray histogram represents the number of objects with respect to its altitude. And there are several dots on the histogram. So a red dot means the optical payload satellite in orbit, and blue dot means the radar payload. And green dot means the near future mission. So this KARI constellation operate or be operating in area of 500 to 900 kilometers in altitude. And this is about geostationary satellites. So we currently operating three geostationary satellite, COMS and GK2A and GK2B. So near our satellite, there are Japanese and Russian and Laos satellites. So we try our best to keep these satellite in our station keeping box. Okay, to safe operation for KARI constellation, we are do conjunction assessment activity 24 hours and 7 days. We using the CA FAST tool, conjunction assessment fluid automation support tool since 2016, and we did upgrade this tool this year. So it has a conjunction assessment function and collision avoidance maneuver planning and external interface with CSPAC and LEO labs, and it has also automated documentation and statistics. So we mainly using the CDM of CSPAC. Yeah, that is the primary data source, and we also using LEO Labs CDM as a supplementary purpose. And if we perform the final assessment, we can use our precise ephemeris. So this is the simple statistics in 2022. So we have 3 criteria: course assessment and final assessment and collision avoidance maneuver. So we performed the course assessment 279 event, and the specific criteria is below: the prediction day and minimum range and radial distance and collision probability. And we also performed final assessment 156 event, and finally we did 1 collision avoidance maneuver for COMSAT 5. So that is our mitigation workflow. So the CDM means the input data. So we have several conditions. So as you can see in the table, so we have various conditions for that, and then if specific event satisfies some condition, so we move to the next phase. So yes, when specific event satisfy the condition 1, TCA, time to closest approach, and minimum range, radial distance, move to the level 1. So we do final assessment, and FOT report means flight operation team report. So there are a lot of people for the operation of satellites. So I inform them that the collision avoidance maneuver may be happen in near future. So we should prepare about that. Yeah, that is the FOT report. And then we should upload our precise ephemeris to the CSPAC. Yeah. And then if condition 3 was satisfied, we move to the level 2. So collision avoidance maneuver, and then level 3, emergency call, state of health monitor, and level 4, end of life. So fortunately, cardiac constellation, all satellite have its thrusters, so it can perform the collision avoidance maneuver. So we have no event level 3 or level 4 so far. Yeah. So this is our tool GUI. So CAFast main GUI. So we can easily check the conjunction status from CSPAC or LeoLabs data. And this is the geometry analysis view. So we can easily understand that this geometry situation, relative position, and covariance information from CDM. And this is about collision avoidance maneuver planning. So the ultimate goal of collision avoidance maneuver planning is to find out the proper burn start time and burn duration. So the value of the heat map means the minimum range. So the bright side is safe and dark side means the risky. So we can select the various selection of them. And this is about breakup simulator for sudden on-orbit breakup event. We developed these tools 2 years ago because of Russian ASAT test. So from this, we built this tool based on the NASA, the breakup model Evolve 4. Orbit specific orbital fragment. So using this orbit information, we can perform the course assessment for Cardi constellation. So here is future plan. So we performed the upgrade our tour this year. However, the space environment, space object environment is changing dramatically. So we should keep upgrading our tool for increased automation function and capacity growth. Yeah, because we have planned for constellation mission, like 11 satellites or 40 satellites. So many satellites we should operate in the near future. So we need to increase our capacity. And then SSA and STM research is also important. So measurement for SSA, STM, like a radar or passive RF in ground infrastructure and data sharing technology to prepare our space traffic management. And metaverse and digital twin technology is also important. And OOS, on-orbit servicing, is also important. That's all. Thank you for listening to my presentation.
Thank you very much, Jaedong Song, for that fantastic presentation. So our third and final speaker is Mike Lindsay from Astroscale. So Mike is Chief Technology Officer at Astroscale, based in Tokyo, I believe, a role he has held since 2020. In this role, Mike is responsible for driving the company's overall technical strategy and shaping future services and mission architectures. If you don't already know, Astroscale is a great company with a global presence, providing on-orbit servicing and debris removal services. I believe, Mike, you might have a technology demonstrator which is ready to launch from my very own New Zealand. I'm sorry that maybe hasn't happened yet, but I hope it will soon. Really exciting. And before Astroscale, Mike has one of the most impressive CVs I've seen in a long time, having worked in various roles at OneWeb, Google, and NASA. So, Mike, over to you.
Yeah, thank you very much, and thank you for this opportunity to contribute to this discussion. I also have some slides to share. I'll pull those up right now. Okay, hopefully that's all right. There we go. All right, great. So yeah, I thought I'd take this opportunity to introduce Astroscale, what we're working on, and highlight how some of the services and technologies we are developing contribute to space sustainability, and as a follow-on effect, enhance space traffic management. So, as Isaac mentioned, Astroscale is a global company. We have offices in 6 locations around the world. About 500 people. I'm based in Tokyo, which is where our headquarters is. Astroscale's vision is the safe and sustainable development of space for the benefit of future generations. And the way in which we achieve this vision is through innovating technologies, looking at how we can advance the economies that support space sustainability, and then making sure we're informing and helping formulate policies that foster this support and enable things like in-orbit services or responsible norms of behavior globally towards this ultimate goal of space sustainability. So in my role, I'm focusing on the technology aspect of that. So I wanted to highlight some of the technological capabilities that we've been building at Astroscale. And what you see on the screen here is a list of various services that we have. So starting from the left is life extension fleet management. This is a service where we have a servicer spacecraft that can dock with a GEO client, say 2 to 4 tons in geosynchronous orbit, and provide station keeping, maneuverability, or salvage where we can save their orbit position and make sure that they're continuing to provide their service. And what that does is reduces the amount of launches. It reduces the amount of waste in case that satellite cannot dispose of itself. The next service is in-space situational awareness or inspection. This is the ability to rendezvous with a client, be it a derelict object in space or perhaps a spacecraft that has suffered an anomaly, So we can provide visual data on that object to say, okay, what's going on? How is it behaving? We can also get some information about the environment if we look at if there's damage that was done by other space debris, and send that data down to help us better understand how spacecraft behave in the environment, and then come up with an action plan to either remediate that object or come up with some other solutions. Orbital transfer just means we can dock with an object and move it to a desired orbit. And if you take that to the extreme, active debris removal is just the orbital transfer, taking an object from its orbit and then dropping it off so it can decay into Earth's atmosphere and burn up. So that's the active debris removal service, where we can remediate the environment, actually take debris objects from high traffic areas and make sure that they no longer pose a risk to safe operations. And then looking into the future, we are looking at how to develop services such as refueling, maintenance, and repair, and maybe someday recycling. And these are all very attractive services because they all contribute, again, to that circular economy, which is kind of depicted on the right-hand side of the slide. I apologize, there's a lot of information on the slide, but I'm just going to highlight some of the graphics for time. So on the right-hand side, we have, we're focusing on reuse, repair, recycle, regenerate, remove, reduce. These are activities that we've highlighted that really contribute, again, to the circular economy in space. So the services we're developing right now and we're demonstrating contribute to this, but you can see on the kind of the right lower half of that, these are future capabilities that we don't have yet, but we're working towards. But they all have the same core capability, which is based on the ability to rendezvous, dock with a client, and then either move it or manipulate it or provide some sort of service. So that's the core that we're focusing on right now, and we'll expand from there as we get more support, as in-orbit servicing becomes more mainstream and expected. So a look at some of the missions that Astroscale is working on right now. ELSA D at the top is one that we've launched already. That was launched in 2021. That was a technology demonstration mission, and I'll have a few more slides where I'll go into detail about what we accomplished with this mission. Address J, as Isaac mentioned, that spacecraft has been shipped to New Zealand, and it is awaiting launch. It will launch on a Rocket Lab Electron. And this mission will inspect a derelict rocket body that is in space right now. So this will be the first time a commercial company will rendezvous with a piece of debris and take some imagery of that. It's intended to be a precursor to our actual removal mission, but we're just checking it out right now, seeing how it looks, how is it spinning, and this will give us information on how to better approach it and then grab it and eventually deorbit it. ELSA M and Lexi and Cosmic represent activities out of the UK and the US, and both these missions are in LEO and in GEO, and they represent scaling up our production. So moving from more of a demonstration or bespoke government mission to more of a high volume commercial solution for our servicers. So more about ELSA D. This is the one we launched in 2021. As you can see on the right, this spacecraft before launch was configured. It's actually two spacecraft that are connected. The smaller spacecraft is the box on top. Actually, I wonder if I can get my cursor to show up here. Yeah, so up here on the top is a client that we launched together with the servicer. And what we did after launch is we separated these two objects and then performed tests to make sure we could rendezvous with the client and then capture with this magnetic capture system that you see here. So that was a successful demonstration. We did relative station keeping. But a magnetic capture device only works if the client object is prepared with a ferromagnetic docking plate. Of course, in this case, that's how we launched it. But in order for this to be a more long-term sustainable solution for the space industry at large, we need we'd like to see a broader adoption of this idea of preparation. So before you launch a satellite, you have kind of sustainability in mind, and you invest in preparing satellites for in-orbit servicing. And a docking plate is one such way you could do that. When you have this known interface, now the servicer knows how to dock with it. It knows it's safe. We have technology that is compatible with that, and now we can do end-of-life services or other repair services once we have that docking point. So this is what we were trying to demonstrate with ELSA-D. It's what we did. And this notion of thinking about sustainability in various phases of the life cycle is depicted here. So right from the beginning, satellite design, you're thinking, okay, how do we design a spacecraft in a sustainable manner? And I'm speaking for what we think should be embraced by the entire space industry, not just astroscale. So how are satellites designed with the end of life or sustainability in mind? And then pre-launch, okay, what are the practices that we need to bake into our operations plan, a launch plan? How do we design a constellation, for example, in the most sustainable way? Operations, when you're actually doing the activities, you're coordinating your operations, collision avoidance, for example. Then end of life, what's the most responsible way to dispose of the satellite? And in some cases, when it's not necessarily possible, what are the other options? That's where preparation for in-orbit servicing comes into play. We're seeing this type of mentality already adopted by some players, such as OneWeb. So what you're seeing here is an actual picture of OneWeb satellites with a ferromagnetic docking plate on board all of their spacecraft. So there's hundreds of these up there now. And Astroscale has their own design as well that we are advocating. This is our ferromagnetic docking plate. I don't want this to come across as a sale pitch. I'm not trying to sell docking plates, but it's more about fostering this idea of thinking about the future, thinking about, okay, if things go wrong, how do we make sure that we can remediate the environment in the future? And this is just one example of that proactive mindset towards sustainability, and that we're developing solutions for, and the other contributors to this panel are also part of that solution. So happy to be part of this discussion. Thanks again for the opportunity.
Fantastic. Three really great presentations. And I just want to say thank you to all of you for those fascinating insights. So we have some time now, and since we don't have any questions on the Q&A, I will ask some questions. So Tanvir, first a question for you. I'm going to focus on the part of your business that fuses data together from multiple different sources. I think we've all seen the emergence of more data around space situational awareness, which I think is a very positive thing. But surely there must be some challenges in taking different types of data from different providers, mix of government, non-government, commercial. What challenges do you find in bringing those different data sources together and turning them into insights for customers?
When it comes to data sources, there are usually two data sources from government catalogs or from private catalogs like the ones that we are in. When it comes to government catalogs, sometimes every government likes to use their own object identifying number. For example, US has NORAD ID and Russia has their own satellite catalog ID. And every nation has their own way of identifying the object. And there is many times when it comes to government catalogs, no straight correlations between the different IDs. So there might be 1, 2, 3 IDs in country A. There might be A, B, C ID in from country B. We don't know whether A is 1 or B is 1 and things like that. So there's no straightforward way of mapping catalogs coming from two different countries. So I think when it comes to utilizing data from governments, that's the biggest challenge. And when it comes to private companies or in general, this is applicable for both government and private, is the kind of data that we get. Most of the time, the data that we get is, I would say, post-processed or has a lot of analytics that has already happened. It comes either in form of, let's say, TLE, that is why many of us would have used TLEs, or in form of state vectors. If you're getting data in form of TLEs, there is very little value addition that can be done when it comes to data fusion, although data fusion can be done, but utilizing data in TLEs format is challenging for when it comes to fusion. When data is given in terms of state vectors, that is essentially much more accurate way. TLEs are, when we compare accuracies of TLEs and state vectors, we have 10x improvement when it comes to state vectors. So when we get data in terms of state vectors, it's easier to fuse it. And if we take a step back, the raw data that is gathered by a sensor or space-based or ground-based. Getting the data in its raw format is best for data fusion, and the primary challenge there is clear definition or understanding of coordinate systems, because even a 10 arc seconds of misunderstanding in when it comes to coordinate systems, that means the data cannot be transformed from raw data to operational picture. That means the data is useless. So, so understanding the coordinate systems used from the sensor and translating that coordinate systems to the operational picture, that is the most important part, is what I would say.
Yeah, fantastic. Thank you. That's a really good explanation, I think, of some of the challenges. So my next question is to Jaedong Song. So you explained really effectively how Kari does the analysis, how you do the analysis for conjunctions, and then the process that you take to make a decision to maneuver. What I would like to understand is, how do you take into account the actions of other satellite operators? So when you're talking about two active satellites, how do you take into account or interact with another satellite operator who's also making a decision about whether to maneuver?
Yeah, great question. So actually, it is hard to interact directly to another space operator so far. So we have only one case to cooperate this same conjunction event. We about 6 years ago, we contact with the NASA Kara team, because our satellite and their space asset is closed, very closed. So at that time, they email us, and then we discuss using email. But now, we now using indirect the method. We upload our precise orbit to CSPAC, and then CSPAC gathering these satellite owners' precise information, and then they recalculate and distribute or modify the CDM or modify the conjunction result. So we get that information. So yes, but we need to improve these structures. So what if we can directly connect it to other space operator? It could be more efficient and more time efficient. Yeah, so that is important thing. So we try the technology to communication to other space owner and operator, like a metaverse technology or digital twin technology. Yes.
Yeah, interesting challenge, and interesting example as well to use. Okay, so Mike, lucky last. So I want to ask you, and take advantage of the fact that you're the global CTO, and Astroscale has a presence across the world. So I would like to ask you a question about policy. I know that you focused in your presentation on the technology side, but what do you expect from governments in terms of facilitating this this more, I guess, I won't say environmentally friendly, but it's a different mindset about thinking about the life cycle of satellites from start to finish. And I think your different technology products capture the different life cycle parts really, really well. What are you expecting from government policy? And maybe I'd be interested in how you see that from across the world, given Astroscale's global reach.
Yeah, that's a great question. So from an operator perspective, let's say that's not doing the servicing, but utilizing space for broadband connectivity or imagery or other services, space sustainability should be seen as an investment and not an expense. What we typically see, though, is that events that unfold in space take place over many years, if not decades. We're in a worsening environment that is apparent, but the degree to which that gets worse is not necessarily falling within a 6-month or a year timeline, or in some cases a few years that most commercial companies may be considering in their risks, for example. So investing in the long-term sustainability is not always at the forefront of minds of the designers. And so what governments can do is kind of better foster that mindset. And then in some cases, when there's opportunities to provide some financial support or investment or other mechanisms, that support that mentality, that investment in sustainability. Because again, we need to be thinking about the long term. That means right now we need to make some investments. And so that, it's not necessarily trivial to invest in sustainability today, but it pays off for everyone. And because space is a global resource, and every government plays a part in managing that resource, that's where we need to see some action. From a servicer point of view, what we'd like to see is make sure that our activities are thought of and enabled through licensing regimes. So rendezvousing with a derelict satellite or grabbing another satellite is not always covered in the regulations. I know a lot of nations are developing new policies that support this activity. New Zealand is one of them that released some policies recently that support these types of activities. So we'd like to see more of that. Spectrum is another big consideration, because the way in which a servicer utilizes spectrum is actually quite unique compared to more legacy types of missions. Because we're moving orbits quite a bit, we're using lots of bandwidth when we're doing rendezvous, and we have a changing attitude. These types of activities haven't been, I think, well analyzed by the ITU, for example. And actually, what just came out of the Radio Communications Assembly in Dubai just a couple of weeks ago was a new resolution that's calling for studies on these types of activities. It explicitly mentions in-orbit servicing, active debris removal. So that's a good opportunity to start thinking about, okay, how, as a government, how do we support the analysis of requirements that in-orbit servicing needs to achieve their mission? Because again, it's important for space sustainability. Your last part was about how this is different between administrations. Certainly in the countries where Astroscale is right now, we've seen a lot of support for these activities, but it's actually different between each of them. So in one country, it's easier to license our mission. In another country, it's easier to license their spectrum. Some countries have different funding mechanisms. Some countries don't have any money available to advance this technology. I could go on for a long time about the specifics, but just to generalize it, I think the biggest concern right now is the lack of harmonization. I think that's the real key. We need to see, spectrum is maybe the best example of harmonizing spectrum access, because we need to be able to use that in land in multiple different countries. But also, if we want to start servicing spacecraft from different countries with a servicer from Japan, for example, that could be really tricky if those regulations for that specific country don't exist. So, yeah, that's the bottom line, perhaps. Thanks.
Yeah, thank you so much, Mike. And I think that's actually a good note to maybe conclude, because as you note, and as you have all noted, this is not, as we know, all of us, being interested in this issue, it's not a problem that a single country can solve. It's not a problem that any single entity can solve with a new technology. And I think what we see is from all three of you is a call for, I think, more harmonization, whether that's around spectrum or data standards and labeling, funding, regulation, and policy, or even just better methods of communicating directly between satellite operators. So from my perspective, I think, as a policy person, this has been really useful for me personally, but I want to just thank you for contributing to this wider process, the Summit for the Future process. I know that large multilateral processes can be hard to follow. It's hard to see sometimes how they make change, but change does come gradually and slowly. And the most important thing is that these processes are how we get global change, not just change within one or two countries. And I think what we can all see today from these presentations is that change, it's global. It needs to be global by default, and not restricted to just one or a small group of countries. So with that, I would just like to say one last big thank you to the presenters. Thank you to Mike, to Jae-Dong Song, and to Tanvir. Thank you very much for taking the time out of your day, morning or evening, depending on where you are. Thank you very much to Portugal Space for being the host, to Inez for being the rapporteur. And I guess we will conclude the session there. Just a very big thank you to you, and of course to our listeners as well. So thank you very much, and I hope you enjoy the rest of your day or your evening.
Thank you very much.
Thank you very much, Isaac. Thank you very much to all of our speakers for being here for this very interesting session. On our side, we'll come back for the second session at 12 p.m. See you soon. Thank you, everyone.